Have you ever wondered what secrets lie hidden in the darkness between Mars and Jupiter, floating silently in that vast graveyard of celestial debris we call the asteroid belt? Tonight, we're embarking on a journey to one of the most mysterious and potentially life-harboring worlds in our solar system. A world that NASA's groundbreaking discoveries have revealed to be far more extraordinary than anyone ever imagined. Welcome to the story of Ceres, the closest dwarf planet to Earth, and the stunning revelations that are rewriting everything we thought we knew about the potential for life in our cosmic neighborhood. I'm absolutely thrilled you've joined me for this exploration, because what we're about to uncover together will fundamentally change how you think about the possibility of alien life existing right here in our own solar system. Before we dive into these mind-blowing discoveries, I'd love to know where you're watching from tonight. Drop your location in the comments below. There's something beautifully fitting about discussing distant worlds while we're all scattered across different time zones on our own pale blue dot. Whether you're watching the stars emerge in your corner of the world, or perhaps it's morning where you are with sunlight streaming through your window, we're all united in our curiosity about what lies beyond our home planet. Now, if you find wonder in these cosmic revelations and enjoy diving deep into the mysteries of space exploration, I'd be incredibly grateful if you'd consider hitting that subscribe button and giving this video a thumbs up. It genuinely helps the algorithm find more curious minds like yours, and it supports the time and research that goes into bringing you these fascinating stories. Here's what makes this story absolutely extraordinary. For decades, scientists viewed Ceres as nothing more than a large asteroid, a rocky remnant from the early formation of our solar system. But when NASA's Dawn spacecraft arrived at this distant world in 2015, it didn't just visit another space rock. It discovered an active, dynamic world that may have once harbored the perfect conditions for life to emerge and thrive. We're talking about a world where ancient oceans once existed beneath an icy crust, where mysterious bright spots shine like beacons across a dark landscape, where water vapor still escapes into the thin atmosphere, and where recent geological activity suggests this world is far from the dead, frozen rock we once believed it to be. But perhaps most incredibly, NASA's latest research suggests that billions of years ago, Ceres may have possessed something that scientists consider absolutely crucial for the emergence of life, a long-lasting source of chemical energy that could have sustained living organisms in its hidden depths. This isn't science fiction. This is cutting-edge science that's forcing us to expand our understanding of where life might exist in the universe. Tonight, we're going to explore how a world that's smaller than our moon, sitting in the cold depths of space between Mars and Jupiter, became one of the most promising candidates in our search for signs of ancient or even current microbial life. The story begins with a world that defied expectations from the very moment we got our first close look at it. Ceres isn't just the largest object in the asteroid belt. It's a world that comprises 25% of the entire asteroid belt's mass, making it a gravitational giant among the cosmic rubble that surrounds it. But size isn't what makes Ceres special. What makes it extraordinary is what lies beneath its mysterious crater-scarred surface. Picture this: a world that's roughly 600 miles across, about 1/4 the diameter of our moon, spinning nearly perfectly upright through space with almost no seasonal variation. a world where a day lasts just over 9 hours, where the distant sun appears as nothing more than a bright star in the perpetual twilight sky, and where temperatures plunge to -160 degrees Fahrenheit. This is Ceres as we first understood it, a cold, distant, seemingly lifeless world. But appearances, as we're about to discover, can be profoundly deceiving. When Giuseppe Piazzi first spotted Ceres through his telescope in 1801, he had no idea he was looking at what would eventually become one of the most fascinating worlds in our solar system. For over 2 centuries, this distant object was classified as an asteroid. Just another piece of debris left over from the chaotic early days of planetary formation. Scientists believed it was nothing more than a large rock, cold and dead, with perhaps some water ice mixed into its composition. Everything changed when NASA's Dawn spacecraft, after an incredible 8-year journey through the solar system, finally arrived at Ceres in March 2015. Dawn wasn't just any spacecraft. It was a technological marvel, the first probe ever designed to orbit 2 different worlds in a single mission, powered by revolutionary ion propulsion that allowed it to travel farther and stay longer than any previous deep space explorer. As Dawn approached Ceres and began transmitting its first detailed images back to Earth, scientists at NASA's Jet Propulsion Laboratory found themselves staring at something completely unexpected. Instead of the dull, grey, crater-covered rock they anticipated, they were looking at a world dotted with mysterious bright spots that gleamed like jewels against the dark surface. These weren't just 1 or 2 anomalous features. There were over 300 of these brilliant white patches scattered across Ceres's surface, each one shining with an intensity that suggested something far more complex was happening on this distant world. The most prominent of these bright features lay within a massive crater called Ocata, a stunning geological formation 57 miles across and 2.5 miles deep. At the center of this ancient impact site, a cluster of brilliant white deposits reflected sunlight with an intensity that was absolutely mesmerizing. Scientists quickly realized they weren't looking at ordinary rock or even typical space ice. They were observing something that suggested active geological processes were still shaping this supposedly dead world. But the bright spots were just the beginning of Ceres's surprises. As Dawn settled into increasingly lower orbits, mapping the dwarf planet's surface with unprecedented detail, it became clear that this world was far more geologically active than anyone had imagined. The spacecraft detected water vapor escaping from the surface, evidence of recent geological activity, and perhaps most remarkably, signs that liquid water might still exist somewhere beneath the frozen crust. The implications of these discoveries sent shockwaves through the scientific community. Here was a world that had been largely ignored for decades, dismissed as just another asteroid, revealing itself to be a complex, dynamic environment that challenged everything scientists thought they knew about small worlds in the outer solar system. And NASA's analysis of Dawn's data revealed that those mysterious bright spots were composed primarily of sodium carbonate, a type of salt that forms when briny water evaporates. But here's what made this discovery truly extraordinary. These salt deposits were incredibly young in geological terms, some less than 2 million years old. On a world that's 4.5 billion years old, finding features that are only a few million years old is like discovering wet paint on an ancient monument. The youth of these deposits meant something profound. Ceres had experienced recent geological activity. Somehow, salty water had made its way from deep within the dwarf planet to its surface, where it evaporated in the vacuum of space, leaving behind these brilliant white salt deposits. This wasn't ancient history. This was evidence of ongoing processes that suggested Ceres might still be geologically alive. But perhaps the most mind-blowing revelation came when scientists analyzed the overall composition of Ceres itself. Using Dawn's sophisticated instruments, they discovered that this world wasn't the rocky asteroid they had expected. Instead, Ceres appeared to be incredibly rich in water ice, with some estimates suggesting that its crust might be over 90% ice by mass. This made Ceres one of the most water-rich objects in the inner solar system, containing more fresh water than exists in all of Earth's lakes and rivers combined. The discovery that Ceres was essentially a giant ball of dirty ice hidden beneath a thin rocky veneer completely revolutionized scientists' understanding of this world. Suddenly, they weren't looking at a dead rock floating in space. They were looking at what researchers began calling an ocean world, a celestial body that likely harbored vast amounts of liquid water beneath its frozen surface. This revelation placed Ceres in an exclusive category of worlds that scientists consider prime candidates for harboring life. Until Dawn's mission, this exclusive club included primarily the icy moons of the outer planets, Jupiter's Europa and Ganymede, Saturn's Enceladus and Titan. These distant worlds, warmed by the gravitational pull of their massive parent planets, were thought to be the most likely places in our solar system where life might exist today. But Ceres was different. Unlike those distant moons, Ceres sits in the inner solar system, relatively close to Earth. And unlike those tidally heated worlds, Ceres would have had to generate its own internal heat to maintain liquid water. The question that began to obsess scientists was simple but profound. How could a world as small as Ceres, sitting in the cold depths of space, possibly maintain the conditions necessary for liquid water and potentially life? The answer to this question would lead to one of the most stunning scientific discoveries of the decade, a revelation that would not only explain Ceres's mysterious features, but also suggest that this distant world may have once been one of the most habitable places in our solar system. We're talking about discoveries that could fundamentally change our understanding of where life might arise in the universe, and how many worlds in our cosmic neighborhood might have once been, or might still be, capable of supporting living organisms. Organisms still be capable of supporting living. The breakthrough came when a team of researchers led by Samuel Corville at Arizona State University began developing sophisticated computer models to simulate what had happened inside Ceres over billions of years. Using data collected during Dawn's mission, they created thermal and chemical models that could peer back through time, revealing the hidden history of this enigmatic world's interior evolution. What they discovered was absolutely revolutionary. Their models showed that for the first billion years of its existence, possibly extending up to 2 billion years, Ceres possessed something that scientists had never suspected: a powerfully radioactive core that generated enormous amounts of internal heat. This wasn't just a little bit of warmth. We're talking about a sustained period of intense thermal activity that would have fundamentally transformed the dwarf planet's internal structure and created conditions unlike anything scientists had imagined possible on such a small world. Picture this extraordinary scenario unfolding deep within Ceres billions of years ago. Radioactive elements embedded in the rocky core were steadily decaying, releasing tremendous amounts of energy in the form of heat. This wasn't a brief, violent process like a volcanic eruption. This was a sustained thermal engine that operated continuously for hundreds of millions of years, possibly even longer, gradually warming the entire interior of the dwarf planet from within. The implications of this discovery are staggering when you consider what this internal heating would have meant for Ceres's hidden ocean. Instead of a frozen, static body of water, scientists now believe that Ceres once harbored a dynamic, actively circulating ocean system. Hot water heated by the radioactive core would have risen upward through the rocky interior, carrying with it dissolved minerals, gases, and chemical compounds from deep within the dwarf planet. This creates a picture of ancient Ceres that's almost impossible to reconcile with the cold, seemingly dead world we see today. Imagine vast currents of heated water flowing through the subsurface ocean, creating temperature gradients and chemical mixing processes that would have made this hidden sea remarkably similar to the dynamic ocean environments we find here on Earth. But perhaps most incredibly, this thermal activity would have created something that scientists consider absolutely essential for the emergence of life: hydrothermal vent systems. On Earth, hydrothermal vents represent some of the most vibrant and diverse ecosystems on our planet. These underwater hot springs, where superheated water, rich in minerals and gases, erupts from the ocean floor, support thriving communities of microorganisms that form the foundation of complex food webs. These environments are so rich in chemical energy that life flourishes in the crushing darkness of the deep ocean, completely independent of sunlight and photosynthesis. The thermal models of ancient Ceres suggest that similar hydrothermal systems would have operated within the dwarf planet's subsurface ocean. Hot, mineral-rich water heated by the radioactive core would have erupted through the ocean floor, creating plumes of chemically energized water that could have provided the perfect conditions for microbial life to emerge and thrive. These wouldn't have been occasional, isolated events. The sustained nature of Ceres's internal heating suggests that such hydrothermal activity could have continued for hundreds of millions of years, providing a stable, long-lasting source of chemical energy. But the story becomes even more fascinating when you consider the specific chemistry that would have been involved in these ancient processes. As hot water circulated through Ceres's rocky interior, it would have leached out various chemical compounds, including organic materials that form the basic building blocks of life. Dawn's instruments actually detected organic compounds on Ceres's surface, particularly near a crater called Ernetet, where scientists found evidence of aliphatic hydrocarbons embedded in the rocky material. These organic molecules are particularly significant because they represent the precursor compounds that can eventually form amino acids, the fundamental components of proteins, and ultimately, life itself. The fact that these organic materials appear to be indigenous to Ceres, rather than delivered by asteroid impacts, suggests that the dwarf planet was capable of producing complex chemistry internally, adding yet another piece to the habitability puzzle. The presence of organic compounds, combined with abundant liquid water and a sustained source of chemical energy from hydrothermal processes, means that ancient Ceres possessed all three of the fundamental ingredients that scientists consider necessary for life to emerge. water, organic chemistry, and energy. This places Ceres in an extremely exclusive category of worlds that may have been capable of supporting the emergence and evolution of living organisms. What makes this discovery even more remarkable is the timescale involved. Unlike the brief periods of habitability that scientists have proposed for other worlds, Ceres's thermal models suggest that these favorable conditions could have persisted for an extraordinarily long time. The radioactive heating that drove the dwarf planet's hydrothermal systems operated continuously for possibly up to 2 billion years, providing a stable environment where life could not only emerge, but potentially evolve and diversify. To put this in perspective, life on Earth is thought to have emerged roughly 3.5 billion years ago, and it took nearly 2 billion years for complex cellular life to evolve from the earliest microbial organisms. If Ceres maintained habitable conditions for 1 billion years or more, there would have been ample time for similar evolutionary processes to unfold in its hidden ocean, potentially leading to the development of complex microbial ecosystems. The researchers' models also reveal fascinating details about how this ancient ocean world would have functioned. The circulation patterns driven by thermal heating would have created a dynamic mixing system, constantly bringing fresh nutrients and chemical compounds from the rocky interior up into the ocean environment. This kind of active circulation is crucial for maintaining the chemical gradients that life depends upon, preventing the ocean from becoming stagnant and chemically uniform. Furthermore, the interaction between the hot water and the rocky core would have created what scientists call metamorphic processes, where the heat and pressure transform existing minerals into new chemical compounds. These metamorphic reactions would have released additional gases and chemical energy into the ocean system, further enriching the environment and providing even more potential food sources for hypothetical microorganisms. The thermal evolution models also help explain some of the mysterious features that Dawn observed on Ceres's surface today. The bright salt deposits, the evidence of recent geological activity, and the detection of water vapor escaping from the surface all make sense when viewed as the dying remnants of what was once a much more active and dynamic world. As Ceres's radioactive core gradually cooled over billions of years, the internal heating diminished, causing the once vigorous hydrothermal systems to slowly shut down. However, the process wasn't instantaneous. Even as the primary heat source waned, residual thermal activity continued to drive occasional episodes of geological activity, bringing briny water from the deep interior up to the surface, where it would freeze and evaporate, leaving behind the salt deposits that Dawn observed. These episodes became less frequent over time, but they've continued sporadically right up to the present day, creating the remarkably young geological features that so surprise scientists. This timeline of gradual cooling also explains why Ceres appears to be in a transitional state today, caught between its active past and its frozen future. The dwarf planet still retains vast amounts of water ice in its interior, but most of it is now frozen solid. The small amounts of liquid that remain have become highly concentrated brines, salty solutions that can remain liquid at much lower temperatures than pure water. These briny pockets occasionally find their way to the surface through fractures and weak points in the crust, creating the bright spots and geological activity that Dawn observed. The implications of these discoveries extend far beyond Ceres itself. If a world as small as Ceres could maintain habitable conditions for such an extended period, it suggests that similar processes might have operated on numerous other small worlds throughout our solar system and beyond. Many of the dwarf planets in the outer solar system, objects like Pluto, Eris, and Makemake, formed under similar conditions and likely experienced comparable periods of radioactive heating in their early history. This means that the galaxy might be filled with small worlds that experience long periods of habitability, even if they appear cold and lifeless today. The concept of habitable worlds might need to be expanded to include not just planets in the so-called Goldilocks zone around stars, but also small, icy worlds that generate their own internal heat through radioactive decay. The universe might be far more conducive to the emergence of life than we ever imagined, with countless hidden ocean worlds scattered throughout the cosmos, each potentially harboring the conditions necessary for life to arise and evolve. Life to arise, each potentially harboring the conditions necessary for and evolve. The evidence for Ceres' extraordinary past continues to mount as we examine the specific mechanisms that would have driven these ancient processes. When scientists analyzed the data from Dawn's extended mission, they discovered something that sent shockwaves through the astrobiology community. The chemical signatures detected on Ceres' surface weren't just evidence of water and salt. They were evidence of ammonia-bearing compounds, materials that shouldn't exist naturally in the inner solar system where Ceres currently resides. This discovery points to something profound about Ceres' origins. Ammonia-rich materials form in the cold, outer reaches of the solar system, far beyond the orbit of Jupiter, where temperatures are so low that these volatile compounds can condense and become incorporated into forming worlds. The presence of these materials on Ceres suggests that this dwarf planet didn't form where we find it today. Instead, it likely originated much farther out in the solar system before migrating inward to its current position in the asteroid belt. This migration story adds yet another layer to Ceres' extraordinary history. Picture the chaotic early solar system, a time when massive planets were still settling into their final orbits and gravitational interactions were flinging smaller worlds across vast distances. During this tumultuous period, known as the Late Heavy Bombardment, Ceres was likely a resident of the outer solar system, where it formed with a composition rich in water ice and ammonia compounds. The journey from the outer solar system to the asteroid belt would have been a violent, dramatic process spanning millions of years. Gravitational encounters with the giant planets would have slowly altered Ceres' orbit, gradually spiraling it inward through the solar system until it finally settled into the asteroid belt roughly 4 billion years ago. This migration explains not only Ceres' unusual composition, but also provides crucial context for understanding why this world became so geologically active. You see, the transition from the frigid outer solar system to the relatively warmer inner regions would have triggered profound changes within Ceres' interior. As the dwarf planet moved closer to the Sun, its outer layers would have begun to warm, while the radioactive heating from within continued to generate thermal energy. This combination of external warming and internal heating would have created the perfect conditions for widespread melting and the formation of the subsurface ocean that scientists now believe dominated Ceres' ancient landscape. But here's where the story becomes even more fascinating. The Dawn mission revealed that Ceres' geological activity didn't end billions of years ago when its radioactive heating began to diminish. Instead, evidence suggests that significant geological processes continued much more recently than anyone thought possible. Some of the bright salt deposits that Dawn observed appear to be less than 2 million years old, which in geological terms is practically yesterday. This recent activity points to something remarkable about how small, icy worlds can maintain geological processes long after their primary heat sources have died away. The key lies in understanding how salt affects the freezing point of water. Just as we spread salt on icy roads in winter to prevent freezing, the briny solutions within Ceres can remain liquid at temperatures far below the freezing point of pure water. These concentrated brines act like antifreeze within Ceres's interior, allowing pockets of liquid to persist even as the overall temperature of the dwarf planet continues to drop. Over millions of years, these briny pockets slowly work their way upward through fractures and weak points in the crust, eventually reaching the surface where they create the brilliant white salt deposits that so captivated scientists when Dawn first observed them. The process isn't gentle or gradual. When these pressurized brines finally breach the surface, they can create explosive outgassing events that launch material high into Ceres's thin atmosphere. Dawn actually observed this phenomenon directly, detecting periodic hazes that would appear and disappear around the Ocata crater. Evidence that Ceres is still volcanically active today, though in a very different way than the volcanic activity we see on Earth or other rocky planets. This ongoing geological activity has profound implications for the possibility that life might still exist on Ceres today. While the dwarf planet's surface is far too cold and the atmospheric pressure too low to support liquid water, the subsurface environment tells a different story. Deep within Ceres, protected from the harsh conditions of space, pockets of briny liquid might still exist, potentially maintaining the chemical conditions necessary for microbial life to survive. These deep brines would be incredibly challenging environments for life, highly concentrated with salts and other dissolved materials. However, life on Earth has demonstrated a remarkable ability to adapt to extreme conditions. Scientists have discovered microorganisms thriving in some of the most hostile environments on our planet, from the highly acidic waters of volcanic hot springs to the incredibly salty depths of underground salt mines. The possibility that similar extremophile organisms might exist in Ceres's deep brines represents one of the most exciting frontiers in astrobiology. Unlike the search for life on Mars, which focuses primarily on evidence of ancient microbial activity, the potential for life on Ceres extends to the present day. If organisms did evolve in the dwarf planet's ancient ocean, some descendants might still persist in the protected depths of its interior. But even if no life exists on Ceres today, the dwarf planet's history as a potentially habitable world has revolutionary implications for our understanding of where life might emerge in the universe. The discovery that such a small world could maintain ocean conditions suitable for life for over 1 billion years fundamentally expands the concept of the habitable zone around stars. Traditionally, scientists have focused on the Goldilocks zone, the narrow band around a star where temperatures are just right for liquid water to exist on a planet's surface. But Ceres demonstrates that habitability doesn't require the perfect orbital distance from a star. Instead, worlds can create their own habitable environments through internal processes, maintaining liquid water and chemical energy sources regardless of their distance from their parent star. This realization has profound implications for the search for life beyond our solar system. If small, icy worlds like Ceres can maintain habitable conditions through radioactive heating, then potentially habitable environments might be far more common throughout the galaxy than we ever imagined. Every planetary system likely contains numerous small worlds that experience similar periods of internal heating, creating hidden ocean environments that could have harbored life for billions of years. The Dawn mission's discoveries have also revealed important details about the specific processes that shape these hidden ocean worlds. The spacecraft's detailed mapping of Ceres' surface showed that the dwarf planet lacks the large impact craters that scientists would expect to see on a world that's been exposed to asteroid bombardment for 4.5 billion years. This absence of large craters suggests that Ceres' surface has been reshaped by geological processes much more recently than anyone anticipated. The most likely explanation for this crater deficit is that Ceres' icy crust has been flowing and deforming over geological time, gradually erasing the scars of ancient impacts. This process, known as viscous relaxation, occurs when ice-rich materials slowly flow under their own weight, smoothing out topographical features over millions of years. The fact that this process appears to have operated on Ceres relatively recently suggests that the dwarf planet's interior remained warm and active much longer than theoretical models had predicted. This extended period of geological activity would have had important consequences for any potential life that might have existed in Ceres' ancient ocean. The ongoing circulation of materials between the surface and interior would have continuously refreshed the ocean environment, bringing new nutrients and chemical compounds from the rocky core while removing waste products that might otherwise accumulate and become toxic. Furthermore, the periodic episodes of surface activity would have created temporary connections between the subsurface ocean and the space environment, potentially allowing chemical exchanges that could have influenced the evolution of any resident microorganisms. These episodes might have even provided opportunities for life to spread from Ceres to other worlds through meteorite impacts that could have launched ocean materials into space. The more scientists study Dawn's data, the more they realize that Ceres represents a completely new category of world in our solar system. It's not quite a planet, not quite a moon, and certainly not just an asteroid. Instead, Ceres is something unique, a dwarf planet that successfully maintained ocean conditions suitable for life for an extraordinarily long time, despite its small size and location in the cold depths of space. This uniqueness makes Ceres an invaluable laboratory for understanding how life might emerge and evolve on similar worlds throughout the universe. Every aspect of the dwarf planet's geology, chemistry, and thermal evolution provides clues about the processes that might operate on countless other small worlds scattered across the galaxy. The implications extend beyond just scientific curiosity. As humanity begins to seriously consider the possibility of interstellar exploration, understanding worlds like Ceres becomes crucial for identifying potentially habitable destinations. Small, icy worlds might represent the most common type of habitable environment in the universe, far outnumbering the Earth-like planets that have traditionally captured our imagination. These hidden ocean worlds might also prove to be more accessible targets for future exploration missions. Unlike the massive gas giants of the outer solar system, small worlds like Ceres can be reached with relatively modest spacecraft and can be studied in detail from close orbit. Future missions to Ceres or similar worlds could potentially drill through the icy crust to directly sample the subsurface environment, providing definitive answers about whether these hidden oceans actually harbor life. The Dawn mission has fundamentally transformed our understanding of what makes a world habitable and where we should look for signs of life in our cosmic neighborhood. But perhaps most importantly, it has revealed that the universe might be far more alive than we ever dared to imagine, filled with hidden ocean worlds that could be teeming with microbial life right now, waiting for us to discover them. The discovery of Ceres' potential for past habitability has ignited a new chapter in astrobiology, one that challenges our most fundamental assumptions about where life can emerge in the cosmos. But as we delve deeper into the implications of these findings, we encounter questions that push the boundaries of our scientific understanding and force us to confront the profound mystery of existence itself. Consider for a moment the extraordinary chain of events that would have been necessary for life to actually emerge in Ceres' ancient ocean. The dwarf planet would have needed to maintain not just liquid water, but the precise chemical conditions that allow simple organic molecules to organize themselves into increasingly complex structures. This process, known as abiogenesis, remains one of the greatest unsolved puzzles in science, even when applied to Earth, where we know life successfully emerged. On Earth, the transition from non-living chemistry to living organisms required an intricate dance of molecular interactions, energy sources, and environmental conditions that scientists are still working to fully understand. The emergence of the first self-replicating molecules, the development of cellular membranes, and the evolution of metabolic processes all had to occur in precisely the right sequence under exactly the right conditions. For life to have emerged on Ceres, similar processes would have needed to unfold in an environment vastly different from early Earth. Instead of a surface ocean bathed in sunlight and stirred by atmospheric weather patterns, potential Cerean life would have evolved in the perpetual darkness of a subsurface sea, dependent entirely on chemical energy derived from interactions between water and rock. This scenario isn't entirely without precedent. Here on Earth, scientists have discovered thriving ecosystems in environments that share striking similarities with Ceres' ancient subsurface ocean, deep underground in environments completely cut off from sunlight. Microorganisms have learned to extract energy from chemical reactions involving sulfur compounds, methane, and various minerals. These deep biosphere organisms represent some of the most ancient lineages on Earth, suggesting that life might actually prefer these hidden, chemically rich environments. The hydrothermal systems that likely operated within Ceres' ancient ocean would have created chemical gradients and energy sources remarkably similar to those that support deep-sea life on Earth. Temperature differences between the hot water emerging from the rocky core and the cooler ocean environment would have driven complex circulation patterns, creating micro-environments with varying chemical compositions that could have served as natural laboratories for the emergence of life. But here's where the story becomes even more intriguing. Unlike Earth's deep biosphere, which exists within a planet that also supports surface life, Ceres' hypothetical organisms would have evolved in complete isolation from any surface environment. This isolation would have created unique evolutionary pressures and opportunities that could have led to forms of life unlike anything we see on Earth. The extended timescales involved in Ceres' thermal evolution add another fascinating dimension to this scenario. While Earth's early history was marked by violent impacts, dramatic atmospheric changes, and periodic mass extinction events, Ceres' subsurface ocean would have provided a remarkably stable environment for biological evolution. protected from cosmic radiation, asteroid impacts, and the temperature fluctuations that affect surface environments, life within Ceres could have evolved continuously for hundreds of millions of years without major disruptions. This stability would have allowed for evolutionary processes to unfold in ways that might have been impossible on more dynamic worlds. Given sufficient time and stable conditions, even simple microbial life can evolve remarkable complexity and diversity. On Earth, microbial ecosystems have developed intricate symbiotic relationships, complex chemical communication systems, and sophisticated methods for sharing genetic information that rival anything seen in more complex organisms. The chemical environment within Ceres's ancient ocean would have been particularly conducive to the evolution of what scientists call chemosynthetic life, organisms that derive energy from chemical reactions rather than sunlight. The continuous circulation of mineral-rich water through the hydrothermal systems would have provided a steady supply of chemical reactants, creating an environment where different types of chemosynthetic organisms could have evolved to exploit different chemical pathways. Over millions of generations, these hypothetical organisms might have developed increasingly sophisticated biochemistries, potentially discovering metabolic pathways that terrestrial life has never explored. The unique combination of chemical elements and compounds available in Ceres's environment could have led to entirely novel forms of biochemistry based on different chemical foundations than the carbon-based, water-dependent life we know on Earth. The possibility that such exotic life forms might have existed challenges our understanding of what life actually is and how it might manifest in different environments throughout the universe. If organisms did evolve in Ceres's ancient ocean, they would represent a completely independent genesis of life, a second example of biology emerging from chemistry that could teach us profound lessons about the fundamental nature of living systems. But as Ceres's internal heating gradually diminished over geological time, any life that had evolved in its ocean would have faced an unprecedented evolutionary challenge. The slowly cooling environment would have forced these organisms to adapt to increasingly extreme conditions as their world transformed from a dynamic ocean environment to the frozen, briny pockets that may exist today. This gradual transition presents one of the most fascinating aspects of Ceres's potential biological history. Unlike the sudden mass extinctions that have periodically reshaped life on Earth, Cerean organisms would have experienced a slow, inexorable change in their environment that unfolded over hundreds of millions of years. This timeline would have provided ample opportunity for evolutionary adaptation, potentially allowing life to persist through environmental changes that would have been catastrophic if they had occurred more rapidly. The organisms that might exist in Ceres' deep brines today would represent the ultimate extremophiles, life forms adapted to survive in conditions of extreme cold, high salt concentration, and minimal energy availability. These hypothetical survivors would be the descendants of organisms that successfully navigated billions of years of gradual environmental change, making them potentially among the most evolutionarily resilient life forms in the solar system. The implications of this scenario extend far beyond Ceres itself. If life could persist through such dramatic environmental transitions, it suggests that biological processes might be far more robust and adaptable than we typically assume. This resilience could mean that once life emerges on a world, it might be capable of surviving through cosmic timescales, persisting even as stellar evolution and planetary dynamics fundamentally alter the environments where it originally evolved. This perspective has profound implications for our search for life beyond Earth. Rather than focusing exclusively on worlds that currently exhibit Earth-like conditions, we might need to expand our search to include worlds that may have supported life in the past, even if they appear hostile today. Ancient ocean worlds like Ceres might harbor biological remnants or even active ecosystems hidden deep beneath their frozen surfaces. The technical challenges involved in detecting such life are formidable. Unlike surface life that might be detectable through atmospheric signatures or telescopic observations, subsurface life on worlds like Ceres would require direct exploration missions capable of penetrating through kilometers of ice and rock to sample the hidden ocean environments below. Future missions to Ceres could employ sophisticated drilling technologies similar to those used to explore Earth's deep biosphere or Antarctica's subglacial lakes. These missions would need to carefully sterilize their equipment to avoid contaminating any pristine subsurface environments, while simultaneously carrying sensitive instruments capable of detecting even the smallest signs of biological activity. The search for life on Ceres would also require new approaches to understanding what constitutes evidence of biological processes. Traditional methods for detecting life often rely on identifying familiar biochemical signatures like DNA or specific metabolic byproducts. But life that evolved independently on Ceres might utilize completely different biochemical pathways, requiring scientists to develop more general methods for distinguishing biological from purely chemical processes. These challenges are driving the development of new technologies and scientific approaches that could revolutionize astrobiology. Advanced mass spectrometers capable of identifying complex organic molecules, sophisticated microscopy systems that can detect cellular structures, and novel computational methods for analyzing complex chemical data are all being developed specifically to support the search for life on worlds like Ceres. The potential discovery of life on Ceres would represent one of the most significant scientific breakthroughs in human history. It would provide definitive proof that life can emerge independently in multiple locations, suggesting that biological processes might be a common feature of planetary evolution rather than a rare cosmic accident. Such a discovery would fundamentally alter our understanding of our place in the universe and the likelihood that life exists on countless other worlds throughout the galaxy. But even in the absence of direct evidence for life, Ceres has already transformed our understanding of planetary habitability. The dwarf planet has demonstrated that small worlds can maintain complex, dynamic environments for billions of years, creating conditions suitable for life in locations where no one thought to look. This realization is forcing scientists to reconsider the basic assumptions that guide the search for life and to develop new frameworks for identifying potentially habitable environments. The story of Ceres also highlights the importance of comprehensive planetary exploration in revealing the hidden complexity of seemingly simple worlds. Before the Dawn mission, Ceres appeared to be just another asteroid, unremarkable and scientifically uninteresting. The detailed study of this world has revealed layers of complexity and potential that no one anticipated, demonstrating that even the most humble-appearing objects in our solar system may harbor extraordinary secrets. This lesson extends beyond our solar system to the countless small worlds that likely exist around other stars. The universe may be filled with Ceres-like objects, small, icy worlds that experienced long periods of habitability during their early history. These worlds would be virtually impossible to detect and characterize using current astronomical techniques. Yet they might represent the most common type of habitable environment in the galaxy. The realization that habitability might be hidden within small, seemingly unremarkable worlds has profound implications for how we think about the distribution of life in the universe. Rather than being concentrated on rare Earth-like planets, orbiting in the narrow habitable zones around their stars, life might be widespread throughout planetary systems, thriving in hidden ocean environments that generate their own heat and maintain their own chemical cycles. This perspective suggests that the universe might be far more biologically active than our current methods can detect. Every planetary system might contain dozens of small worlds with subsurface oceans, each potentially harboring unique forms of life that evolved independently from any surface biosphere. The cosmic ocean of life might be vast and largely hidden, waiting for future generations of explorers to discover and study these remarkable hidden worlds. As we continue to analyze the data from Dawn's mission and plan future explorations of Ceres and similar worlds, we stand at the threshold of a new era in astrobiology. The discoveries made at this distant dwarf planet have opened our eyes to possibilities we never considered and challenged us to think more broadly about the nature and distribution of life in the universe. The next chapter of this story promises to be even more extraordinary as we develop the technologies and scientific approaches needed to directly explore these hidden ocean worlds and search for signs of the life that may be thriving in their dark depths. The journey to understand Ceres has become more than just a scientific endeavor. It has become a quest to understand our cosmic context and our place in a universe that may be teeming with life in ways we are only beginning to imagine. Each new discovery brings us closer to answering one of humanity's most profound questions. Are we alone in the universe, or are we part of a vast community of life that spans the cosmos in forms and locations beyond our wildest dreams? The quest to understand Ceres' potential biological legacy has led scientists to examine evidence that would have been dismissed as impossible just decades ago. When Dawn's spectrometers detected complex organic molecules scattered across the dwarf planet's surface, particularly concentrated near the Ernetet crater, researchers initially assumed these compounds had been delivered by asteroid impacts from the outer solar system. But detailed analysis revealed something far more intriguing. The organic materials appeared to be indigenous to Ceres itself, formed through chemical processes operating within the dwarf planet's interior. These weren't simple carbon compounds that might form through random chemical reactions. They were sophisticated aliphatic hydrocarbons, the same types of molecules that serve as building blocks for amino acids and other complex biological molecules here on Earth. The discovery of indigenous organic chemistry on Ceres adds yet another piece to the habitability puzzle. Not only did this world possess liquid water and chemical energy sources, but it also demonstrated the ability to synthesize the organic compounds that form the foundation of all known life. The combination of these three elements, water, energy, and organic chemistry, represents what astrobiologists call the Holy Trinity of habitability. But perhaps even more remarkable than the presence of these compounds is their apparent age and distribution. Unlike organic materials delivered by asteroid impacts, which would be scattered randomly across the surface, Ceres' indigenous organics appear to be concentrated in specific geological formations associated with the dwarf planet's internal processes. This suggests that organic synthesis wasn't a rare, isolated event, but rather an ongoing process that operated for extended periods within Ceres's chemical evolution. The implications of sustained organic chemistry within Ceres extend far beyond simple molecular complexity. On Earth, the transition from simple organic compounds to self-replicating biological systems required countless chemical experiments occurring simultaneously in diverse environments. The more opportunities for chemical experimentation, the greater the likelihood that some of these experiments might stumble upon the precise combination of reactions needed to spark the emergence of life. Ceres's ancient ocean would have provided an ideal laboratory for such chemical experimentation. The hydrothermal systems operating within the subsurface sea would have created countless microenvironments, each with slightly different temperatures, pressures, and chemical compositions. These varied conditions would have allowed different types of organic reactions to proceed simultaneously, creating a vast network of chemical experiments that could have continued for hundreds of millions of years. The sustained nature of these processes is crucial for understanding Ceres's potential biological significance. The emergence of life isn't a simple chemical reaction that either succeeds or fails quickly. It's an incredibly complex process that requires numerous intermediate steps, each building upon the previous ones in an intricate dance of molecular evolution. The longer this process can continue without disruption, the greater the likelihood that it might eventually cross the threshold from chemistry to biology. Recent computer simulations of Ceres's ancient chemical environment have revealed just how sophisticated these processes might have become. As heated water circulated through the rocky interior, it would have created complex chemical gradients that could drive increasingly elaborate reactions. Mineral surfaces within the hydrothermal systems would have acted as catalysts, facilitating chemical reactions that might not occur readily in open water. These mineral-water interactions are particularly significant because similar processes on Earth are thought to have played crucial roles in the origin of life. Clay minerals, sulfide compounds, and various other rock-forming materials can facilitate the formation of complex organic molecules and even primitive cellular structures. The rocky core of Ceres would have contained abundant quantities of such materials, providing countless opportunities for catalyzed organic synthesis. The circulation patterns within Ceres's ancient ocean would have ensured that organic compounds synthesized in the hydrothermal zones were distributed throughout the entire ocean system. This distribution mechanism is essential for the development of biological systems because it allows successful molecular innovations to spread and combine with other chemical developments occurring elsewhere in the environment. Over geological timescales, this process could have led to the accumulation of increasingly complex organic chemistry throughout Ceres's ocean. Molecules that proved particularly stable or reactive would have become more abundant, while less successful chemical experiments would have been broken down and recycled into new combinations. This natural selection of molecular systems represents a crucial step toward the emergence of true biological evolution. The chemical evolution occurring within Ceres's ocean would have been driven not just by random chance, but by the fundamental thermodynamic principles that govern all chemical reactions. Molecules and molecular systems that more efficiently captured and utilized available chemical energy would have become more abundant than those that couldn't compete effectively for resources. This process of chemical competition creates a pathway from simple organic chemistry toward the complex, energy-harvesting systems that characterize living organisms. What makes Ceres' chemical environment particularly fascinating is that it would have operated in complete isolation from any external biological influences. Unlike Earth, where the chemical evolution that led to life was potentially influenced by organic materials delivered from space, Ceres' organic chemistry would have developed entirely through internal processes. This isolation would have created a unique chemical evolutionary pathway that might have led to biological innovations never seen on Earth. The extended timescales available for chemical evolution on Ceres cannot be overstated in their importance. While Earth's early chemical evolution occurred over hundreds of millions of years, it was frequently disrupted by massive asteroid impacts, atmospheric changes, and other catastrophic events. Ceres' subsurface environment would have been largely protected from such disruptions, allowing chemical evolution to proceed continuously for potentially over 1 billion years. This uninterrupted chemical evolution could have led to the development of molecular systems far more sophisticated than anything that existed on early Earth. Given sufficient time and stable conditions, chemical evolution can produce remarkably complex and efficient molecular machinery, even in the absence of true biological systems. Some researchers speculate that advanced chemical evolution might even approach the complexity threshold necessary for the emergence of primitive life forms. The question of whether chemical evolution on Ceres ever crossed that threshold remains one of the most compelling mysteries in astrobiology. The transition from complex chemistry to true biology is still poorly understood, even in the context of Earth's well-documented biological history. The emergence of self-replication, metabolism, and cellular organization represents quantum leaps in complexity that scientists are still working to explain. However, the unique conditions within Ceres' ancient ocean might have been particularly conducive to such transitions. The constant circulation of mineral-rich water would have provided steady supplies of chemical reactants, while simultaneously removing waste products that might otherwise inhibit complex reactions. The thermal gradients created by hydrothermal activity would have provided energy sources that could drive increasingly sophisticated chemical processes. The chemical environment within Ceres' ocean would have been remarkably stable compared to surface environments on most worlds. Protected from cosmic radiation, temperature fluctuations, and atmospheric changes, the subsurface sea would have maintained consistent conditions that allowed complex chemical systems to develop without constant environmental stress. This stability is crucial for the emergence of life, because it allows incremental improvements in molecular systems to accumulate over time, rather than being constantly reset by environmental disasters. The mineral composition of Ceres' rocky interior would have provided additional advantages for chemical evolution. The presence of iron, sulfur, and various other elements essential for biological processes would have ensured that the chemical evolution occurring within the ocean had access to all the raw materials needed to construct increasingly sophisticated molecular systems. The interaction between these elements and the organic compounds synthesized within the ocean could have led to the development of primitive metabolic pathways similar to those used by the earliest life forms on Earth. But perhaps most intriguingly, the gradual cooling of Ceres over geological time would have created a unique evolutionary pressure that doesn't exist on most other worlds. As the internal heating diminished and the ocean environment became progressively colder, any chemical systems that had emerged would have faced the challenge of adapting to changing conditions or facing extinction. This slow environmental change would have created powerful selective pressures, favoring chemical systems that could maintain their organization and function even as their environment became less hospitable. Over millions of years, this pressure could have driven the evolution of increasingly robust and efficient molecular systems, potentially culminating in chemical networks sophisticated enough to qualify as primitive life forms. The possibility that such evolutionary pressures might have operated on Ceres for hundreds of millions of years raises fascinating questions about what kinds of molecular systems might have emerged. Unlike the rapid evolutionary changes driven by competition between different life forms, the evolution occurring on Ceres would have been driven primarily by environmental pressure, potentially leading to highly specialized chemical systems adapted to extreme conditions. These hypothetical chemical systems, if they still exist in Ceres' deep brines, would represent a form of molecular organization unlike anything found on Earth. Evolved specifically to function in extremely cold, salty conditions with minimal energy availability, they might employ biochemical strategies that terrestrial life has never discovered. The study of such systems could revolutionize our understanding of the fundamental principles that govern the organization of complex molecular networks. The detection and study of these advanced chemical systems presents one of the greatest challenges facing future Ceres exploration missions. Unlike living organisms, which often leave clear biosignatures that can be detected relatively easily, complex chemical systems might be indistinguishable from purely inorganic processes using conventional analytical techniques. Future missions to Ceres will need to employ sophisticated new technologies, specifically designed to detect the subtle signatures of organized chemical activity. These might include advanced mass spectrometry systems capable of identifying complex molecular networks, specialized microscopy techniques that can visualize molecular organization, and novel computational approaches that can distinguish between random chemical activity and organized chemical systems. The development of these technologies is driving innovations that extend far beyond planetary exploration. The techniques being developed to search for complex chemistry on Ceres are finding applications in medicine, materials science, and even the development of artificial molecular systems. The quest to understand Ceres' chemical evolution is pushing the boundaries of analytical chemistry and molecular biology in ways that benefit numerous fields of scientific research. But perhaps the most profound implication of Ceres' potential chemical evolution lies in what it suggests about the prevalence of complex chemistry throughout the universe. If a small world like Ceres could maintain sophisticated chemical evolution for hundreds of millions of years, then similar processes might be operating on countless other small worlds throughout the galaxy. This realization fundamentally changes how we think about the distribution of complex chemistry in the universe. Rather than being confined to the rare Earth-like planets that can maintain surface oceans, complex chemical evolution might be occurring throughout planetary systems, hidden within the subsurface environments of small, icy worlds that are far more common than terrestrial planets. The universe might be filled with worlds undergoing their own unique chemical evolution experiments, each developing molecular systems adapted to their specific environmental conditions. Some of these experiments might lead to the emergence of life, while others might produce complex chemical networks that fall just short of true biology, but still represent remarkable achievements in molecular organization. The implications extend to our search for life beyond our solar system. Current techniques for detecting life on exoplanets focus primarily on atmospheric signatures that might indicate biological activity on planetary surfaces. But if complex chemistry and even life are more likely to exist in subsurface environments, then most biological activity in the universe might be completely invisible to our current detection methods. This hidden biosphere concept suggests that the galaxy might be far more biologically active than our observations indicate. Every planetary system might contain numerous small worlds hosting their own chemical evolution experiments, creating a vast network of molecular innovation that spans the cosmos. The total amount of complex chemistry and potentially even life in the universe might dwarf what exists on surface worlds like Earth. The story of Ceres has transformed from a simple tale of a large asteroid into an epic narrative about the potential ubiquity of complex chemistry and life throughout the cosmos. This small world has forced us to expand our definition of habitability, reconsider our assumptions about where complex chemistry can occur, and develop new technologies for detecting the subtle signatures of molecular organization. As we stand on the threshold of a new era in astrobiology, Ceres serves as both inspiration and guide for the discoveries that await us. The techniques being developed to study this remarkable world will soon be applied to similar objects throughout our solar system, and eventually to the countless small worlds that orbit other stars. The dawn of understanding that began with NASA's Dawn mission is still rising, illuminating possibilities that extend far beyond our current imagination. In the hidden depths of a small world that was once dismissed as cosmic debris, we have discovered hints of processes that might connect us to a vast community of chemical evolution spanning the galaxy. Each new piece of evidence from Ceres adds another thread to a tapestry of understanding that is revealing the universe to be a far more chemically and potentially biologically active place than we ever dared to imagine. The journey to understand this remarkable world has become a journey to understand our place in a cosmos that may be teeming with molecular innovation and perhaps even life in forms and locations we are only beginning to comprehend. The implications of Ceres's chemical evolution extend into realms that challenge our fundamental understanding of how complexity emerges in the universe. When we consider the vast timescales over which these molecular processes operated, we begin to appreciate that Ceres wasn't just hosting random chemical reactions. It was conducting a billion-year symphony of molecular innovation that may have approached the very threshold of life itself. Picture the extraordinary laboratory that existed within Ceres's ancient ocean. Countless chemical experiments were running simultaneously across millions of cubic kilometers of subsurface water. Each hydrothermal vent, each mineral water interface, each temperature gradient created its own unique experimental conditions. Some reactions would have failed immediately, their products dissolving back into the chemical soup. Others might have persisted for thousands or even millions of years before eventually breaking down. But here and there, in the vast molecular lottery that was Ceres's ocean chemistry, certain combinations would have struck gold, molecules that could catalyze their own formation, chemical networks that could capture and store energy more efficiently than their surroundings, self-organizing systems that grew in complexity rather than dissolving into chaos. These successful molecular innovations would have gradually accumulated within the ocean environment, creating an increasingly sophisticated chemical ecosystem. What makes this scenario particularly fascinating is that it would have operated according to principles remarkably similar to biological evolution, even in the absence of true life. Chemical systems that were more stable, more efficient, or better at competing for resources would have become more abundant than those that couldn't adapt to their environment. Over millions of generations of molecular reproduction and modification, this chemical selection pressure could have driven the emergence of remarkably sophisticated molecular machinery. The thermal environment within Ceres's ocean would have been perfectly suited for this kind of molecular evolution. The temperature gradients created by hydrothermal circulation would have provided energy sources that could drive increasingly complex chemical reactions. Cooler regions of the ocean would have favored the formation of large, stable molecular structures, while hotter zones near the hydrothermal vents would have facilitated rapid chemical innovation and experimentation. This temperature-driven zonation would have created a natural progression from simple to complex chemistry within Ceres's ocean. Simple molecules formed in the high-energy environment near the vents would have migrated to cooler regions where they could combine into more complex structures. These larger molecules could then circulate back toward the heat sources, where they might undergo further chemical modification before returning to the cooler zones for additional assembly. Over geological timescales, this circulation-driven chemical evolution could have produced molecular systems of staggering complexity. We're not just talking about simple organic compounds like amino acids or nucleotides. The extended time frames available on Ceres would have allowed for the development of large-scale molecular networks that could perform sophisticated chemical functions, potentially including primitive forms of metabolism, information storage, and even self-replication. The mineral-rich environment within Ceres's ocean would have provided additional scaffolding for these complex chemical systems. Clay particles, sulfide minerals, and various crystalline structures would have acted as templates and catalysts, helping to organize complex molecules into functional arrangements. These mineral surfaces could have facilitated the formation of primitive cellular structures, providing the compartmentalization necessary for more advanced chemical processes to develop. Recent advances in understanding how life emerges from non-living chemistry have revealed that the transition isn't as sharp as scientists once believed. Instead of a clear dividing line between chemistry and biology, there appears to be a gradual continuum of increasing molecular complexity and organization. Simple chemical systems gradually develop more sophisticated properties until they eventually cross an arbitrary threshold that we define as life. Ceres's extended period of chemical evolution would have provided ample opportunity for molecular systems to progress along this continuum. Given hundreds of millions of years of stable conditions, chemical networks on Ceres might have advanced surprisingly far toward true biological complexity, even if they never quite achieved the full suite of properties we associate with living organisms. The question of whether these advanced chemical systems still exist within Ceres's deep interior represents one of the most tantalizing mysteries in astrobiology. As the dwarf planet's thermal activity gradually diminished over geological time, the molecular systems that had evolved within its ocean would have faced unprecedented challenges. The slowly cooling environment would have forced these chemical networks to adapt to increasingly harsh conditions or face dissolution. But here's where the story becomes even more remarkable. The chemical systems that managed to survive Ceres' gradual cooling would represent the ultimate achievement in molecular adaptation. Evolved specifically to function in extreme cold, high salinity, and minimal energy conditions, these hypothetical molecular networks would be unlike anything that exists in Earth's biosphere. The briny pockets that may still exist deep within Ceres today could harbor chemical systems that have been continuously evolving for billions of years. These wouldn't be simple organic compounds or even primitive life forms. They would be highly evolved molecular networks, adapted to extract energy and maintain organization under conditions that would instantly destroy any Earth-based organism. The study of such extreme chemical systems could revolutionize our understanding of the fundamental limits of molecular organization. Earth's biosphere, for all its diversity, operates within relatively narrow ranges of temperature, pressure, and chemical composition. The molecular systems that might exist on Ceres today would demonstrate that complex chemistry can persist under conditions far more extreme than anything found in terrestrial environments. This realization has profound implications for astrobiology and the search for life throughout the universe. If molecular complexity can persist and even evolve under the harsh conditions that exist within Ceres today, then similar processes might be operating on countless other worlds that were previously considered completely inhospitable to any form of complex chemistry. The techniques required to detect and study these advanced chemical systems present extraordinary technical challenges. Unlike biological organisms, which often produce clear chemical signatures that indicate their presence, highly evolved molecular networks might be virtually indistinguishable from complex inorganic chemistry using conventional analytical methods. Future exploration missions to Ceres will need to employ revolutionary new technologies specifically designed to detect subtle signs of molecular organization and complexity. These might include quantum sensors capable of detecting minute energy flows within chemical systems, advanced AI systems that can recognize patterns of molecular organization, and sophisticated sampling techniques that can extract and preserve complex molecular networks for detailed study. The development of these technologies is driving innovations across multiple fields of science and engineering. The challenge of detecting complex chemistry on Ceres is pushing researchers to develop new understanding of how molecular systems organize themselves, how energy flows through chemical networks, and how to distinguish between random chemical activity and purposeful molecular behavior. But perhaps the most profound implication of Ceres' potential chemical evolution lies in what it suggests about the nature of complexity itself in the universe. The emergence of sophisticated molecular systems on a small, cold world like Ceres demonstrates that complexity isn't limited to the warm, energy-rich environments that we typically associate with biological activity. Instead, complexity appears to be an emergent property of any system where energy flows through chemical networks over extended periods of time. Given sufficient time and stable conditions, even the most unlikely environments can give rise to remarkable levels of molecular organization and sophistication. This principle extends far beyond planetary science to fundamental questions about how complexity emerges throughout the cosmos. If small worlds like Ceres can host sophisticated chemical evolution, then similar processes might operate on scales ranging from individual asteroids to entire planetary systems. the universe might be permeated with networks of evolving complexity that we're only beginning to recognize. The story of Ceres has evolved from a tale about a large asteroid into a profound meditation on the nature of complexity, evolution, and the potential ubiquity of sophisticated chemical systems throughout the cosmos. This remarkable world has forced us to expand our understanding of what's possible in planetary environments and to develop new frameworks for recognizing complexity wherever it might arise. As we prepare for the next generation of missions to explore Ceres and similar worlds, we stand at the threshold of discoveries that could fundamentally transform our understanding of our place in the universe. The molecular systems that may have evolved within Ceres's hidden depths represent more than just interesting chemistry. They represent a potential glimpse into a vast network of chemical evolution that may span the galaxy. The technologies being developed to study Ceres will soon enable us to search for similar chemical complexity on other small worlds throughout our solar system. Each new detection of sophisticated molecular systems will add another piece to our growing understanding of how complexity emerges and evolves in cosmic environments. The implications extend to our search for life beyond our solar system. If complex chemical evolution is common on small worlds like Ceres, then the galaxy may be filled with countless examples of molecular systems that blur the line between chemistry and biology. Some of these systems may qualify as life by our current definitions, while others may represent entirely new categories of complexity that we don't yet have names for. The universe revealed by Ceres is one where molecular innovation and chemical evolution are ongoing processes occurring throughout space and time. Rather than life being a rare accident that occurred only on a few special worlds, complex chemistry appears to be a natural consequence of planetary evolution that may be happening everywhere conditions permit energy to flow through molecular systems. This perspective transforms our understanding of our cosmic context. We may not be alone in a vast empty universe occasionally punctuated by rare instances of biological activity. Instead, we may be part of a vast community of chemical evolution that spans the cosmos, connecting us to molecular systems and perhaps even life forms scattered throughout the galaxy. The dawn of understanding that began with NASA's exploration of Ceres continues to illuminate new possibilities with each passing discovery. As we develop the technologies needed to study the complex chemistry that may exist within this remarkable world, we're simultaneously preparing to detect and understand similar systems wherever they might exist throughout the universe. The journey to comprehend Ceres has become more than a scientific mission. It has become a quest to understand the fundamental nature of complexity itself and our place within the vast networks of chemical and potentially biological evolution that may permeate the cosmos. Each new insight brings us closer to answering some of humanity's most profound questions, while simultaneously revealing new mysteries that will guide our exploration for generations to come. In the hidden depths of a world once dismissed as cosmic debris, we may have discovered evidence of processes that connect us to the deepest principles governing how complexity emerges in the universe. The chemical evolution that may have unfolded within Ceres's ancient ocean represents more than just an interesting planetary process. It represents a window into the fundamental mechanisms that drive the emergence of order, complexity, and perhaps even consciousness throughout the cosmos. As we continue to analyze the data from Dawn's historic mission and plan future explorations of this extraordinary world, we carry with us the knowledge that we may be studying more than just planetary science. We may be investigating the very foundations of how the universe creates and sustains the complex systems that make existence itself possible. The story of Ceres has become our story, a reflection of the cosmic processes that led to our own existence, and a guide to understanding the magnificent complexity that may be flourishing throughout the universe in ways we are only beginning to imagine. Ways we are only beginning to imagine. The discovery of Ceres as a potentially habitable world has profound implications that extend far beyond our understanding of this single dwarf planet. When we step back and consider the broader picture, we realize that Ceres may represent just one example of a vast category of worlds that have been hiding in plain sight throughout our solar system and beyond. Consider the revolutionary nature of what we've uncovered. For decades, the search for life in our solar system focused primarily on Mars, with its ancient river valleys and polar ice caps, and the icy moons of Jupiter and Saturn, warmed by tidal heating from their massive parent planets. These worlds captured our imagination because they seemed to offer the most obvious pathways to discovering extraterrestrial life. But Ceres has forced us to completely reconsider our assumptions about where habitable environments might exist. Here we have a world that's smaller than our moon, sitting in the cold depths of space far from any major planet, yet it may have maintained conditions suitable for life for over 1 billion years. This discovery suggests that we've been looking for life in all the wrong places, or at least, we've been looking in only a fraction of the right places. The implications become even more staggering when we consider how many Ceres-like objects exist throughout our solar system. The asteroid belt alone contains millions of rocky and icy bodies, many of which formed under similar conditions to Ceres. While most of these objects are much smaller than Ceres, size isn't the only factor that determines a world's potential for maintaining subsurface oceans. The key insight from Ceres is that radioactive heating can sustain habitable conditions for extraordinary lengths of time, even on relatively small worlds. This heating depends on the initial composition of rocky materials during planetary formation, and many objects in the asteroid belt would have started with similar radioactive inventories. Some might have been too small to maintain heating for extended periods, but others might have been large enough to sustain their own periods of habitability. Even more intriguingly, the outer solar system contains vast populations of small icy worlds that could have experienced similar thermal evolution. The Kuiper Belt, that distant realm beyond Neptune's orbit, hosts thousands of known objects and potentially millions more that remain undiscovered. Many of these worlds are similar in size to Ceres, or even larger, and they formed in environments even richer in water ice and organic materials. These distant worlds would have experienced their own periods of radioactive heating, potentially creating subsurface oceans that could have persisted for billions of years. Unlike Ceres, which migrated inward from the outer solar system, these objects remained in the cold outer reaches, where their icy compositions would have been preserved more effectively. They might represent even better examples of hidden ocean worlds than Ceres itself. The dwarf planets of the outer solar system, worlds like Pluto, Eris, Makemake, and Haumea, all likely experienced significant periods of internal heating during their early history. Recent observations have revealed that several of these worlds show signs of geological activity that may be driven by subsurface oceans. Pluto's nitrogen glaciers and complex surface chemistry suggest ongoing geological processes that require internal heat sources. But the implications extend far beyond our own solar system. If small worlds like Ceres can maintain habitable conditions through radioactive heating, then potentially habitable environments might be extraordinarily common throughout the galaxy. Every planetary system likely contains numerous small rocky and icy bodies that formed with radioactive materials embedded in their interiors. Unlike the traditional habitable zone concept, which restricts potentially life-bearing worlds to narrow orbital ranges around their host stars, radioactive heating creates habitability that's independent of stellar distance. A small, icy world could maintain subsurface oceans, whether it orbits close to its star or drifts alone through interstellar space. This dramatically expands the number of potentially habitable environments in the galaxy by orders of magnitude. Consider the implications for exoplanet science. Current techniques for detecting and characterizing planets around other stars are biased toward finding large worlds that orbit close to their host stars. These methods are excellent for discovering hot Jupiters and super-Earths, but they're completely blind to the small, distant worlds that might be the most common sites for life in the universe. The vast majority of potentially habitable worlds might be small icy objects that would be impossible to detect using current astronomical techniques. These worlds wouldn't produce detectable atmospheric signatures or cause measurable stellar wobbles. They would remain completely invisible to our most sophisticated planet-hunting instruments, yet they might outnumber detectable exoplanets by factors of millions or billions. This realization forces us to confront the possibility that most life in the universe exists in environments that we cannot observe and may never be able to study directly. The cosmic census of life might be dominated by microbial ecosystems thriving in hidden oceans scattered throughout planetary systems, completely disconnected from the surface worlds that capture our attention. The timescales involved in these hidden biospheres add another dimension to their potential significance. While surface environments on most worlds are subject to dramatic changes over geological time, subsurface oceans provide remarkably stable conditions for biological evolution. Life that emerges in these protected environments could potentially evolve continuously for billions of years without major disruptions. This stability would allow for the development of biological complexity that might be impossible to achieve in more dynamic surface environments. Given sufficient time and stable conditions, even simple microbial ecosystems can evolve remarkable diversity and sophistication. The hidden ocean worlds of the galaxy might host forms of life that have had billions of years to develop complex ecological relationships and sophisticated biochemical capabilities. The isolation of these subsurface biospheres would also lead to completely independent evolutionary pathways. Each hidden ocean would represent a separate experiment in biological evolution, potentially leading to forms of life that utilize different biochemical strategies than anything found on Earth. The total biological diversity hidden within subsurface oceans throughout the galaxy might dwarf the diversity found in all surface environments combined. This perspective has profound implications for how we think about the search for extraterrestrial intelligence. If most life in the universe exists in hidden subsurface environments, then the development of technological civilizations might be far more challenging than we typically assume. Subsurface life would have no direct access to space or even to their planetary surfaces, making the development of astronomy and space technology extremely difficult. However, this doesn't mean that subsurface civilizations are impossible. Given billions of years of continuous evolution, life in hidden oceans might develop capabilities that we can barely imagine. Highly advanced biological systems might be able to manipulate their environments in ways that eventually allow them to reach planetary surfaces, or even develop forms of technology adapted to their unique circumstances. The possibility that advanced life exists in hidden oceans throughout the galaxy raises fascinating questions about how such civilizations might communicate or interact with the surface universe. Perhaps some of the unexplained phenomena we observe in space are actually signatures of advanced subsurface civilizations that have found ways to project their influence beyond their hidden ocean environments. The study of Ceres has also revealed important insights about how these hidden ocean worlds might be interconnected through cosmic processes. The discovery of organic compounds and evidence for complex chemistry on Ceres suggests that these worlds aren't completely isolated. Material can be exchanged between different objects through impact events that launch debris into space, potentially carrying chemical signatures or even biological material between different hidden ocean worlds. This possibility raises the intriguing prospect that life might spread between different subsurface environments through natural cosmic processes. A single genesis of life in one hidden ocean could potentially seed numerous other worlds throughout a planetary system, creating networks of related biospheres that share common evolutionary heritage while developing in isolation from each other. Over cosmic timescales, this process could lead to the emergence of vast biological networks spanning entire regions of the galaxy. Individual hidden ocean worlds might serve as nodes in a galactic biological web, connected by occasional exchanges of material through impact events and gravitational interactions. The total scope of biological activity in the universe might be far more interconnected and extensive than anything we can currently observe. The technological implications of understanding hidden ocean worlds are equally profound. As humanity develops more advanced space exploration capabilities, these subsurface environments represent some of the most accessible targets for detailed astrobiological investigation. Unlike the surfaces of distant exoplanets, hidden ocean worlds in our own solar system could potentially be reached and studied directly using robotic exploration missions. The development of technologies for penetrating planetary ice shells and sampling subsurface oceans would open entirely new frontiers in astrobiology. These techniques could be applied not just to Ceres, but to dozens of other potentially habitable worlds throughout our solar system. Each successful mission would add new pieces to our understanding of how life emerges and evolves in hidden ocean environments. The scientific instruments and analytical techniques being developed for hidden ocean exploration are driving innovations that extend far beyond planetary science. Advanced life detection technologies, sophisticated chemical analysis systems, and revolutionary drilling and sampling techniques are finding applications in fields ranging from environmental monitoring to medical diagnostics. But perhaps most importantly, the study of hidden ocean worlds is forcing us to develop new theoretical frameworks for understanding life itself. The extreme conditions that exist in subsurface oceans challenge our basic assumptions about the limits of biological activity and the requirements for habitability. Life that evolves in these environments might operate according to biochemical principles that we haven't yet discovered. The investigation of Ceres and similar worlds is pushing the boundaries of astrobiology toward a more universal understanding of how complex systems emerge and evolve in diverse environments. Rather than focusing exclusively on Earth-like conditions, scientists are developing broader theories that can encompass the full range of physical and chemical conditions where life might potentially arise. This expansion of our theoretical understanding has implications that extend beyond biology to fundamental questions about the nature of complexity itself in the universe. The emergence of sophisticated chemical and biological systems in hidden ocean worlds demonstrates that complexity is far more robust and adaptable than we previously understood. These discoveries are contributing to new insights in fields ranging from systems biology to artificial intelligence. The story of Ceres has become a catalyst for rethinking some of our most basic assumptions about life, complexity, and our place in the cosmic order. What began as the study of a large asteroid has evolved into a comprehensive investigation of how the universe creates and sustains complex systems under conditions that were once thought to be completely hostile to any form of organization. As we continue to analyze the wealth of data returned by the Dawn mission and plan future explorations of Ceres and similar worlds, we're simultaneously developing the conceptual tools needed to understand a universe that may be far more biologically active than we ever imagined. The hidden ocean worlds scattered throughout the galaxy represent more than just interesting targets for future exploration. They represent a fundamental challenge to our understanding of life's place in the cosmic hierarchy. The implications ripple outward from planetary science to philosophy, challenging us to reconsider what it means to be alone in the universe, when that universe might be teeming with life in places we can't see and forms we can't yet imagine. The cosmos revealed by Ceres is one where biological innovation and chemical evolution are ongoing processes occurring on scales and in environments that dwarf anything we've previously considered. This perspective transforms our relationship with the universe itself. Rather than existing as isolated biological accidents on a rare habitable planet, we may be part of a vast community of life that spans the galaxy in forms and locations that stretch our imagination. The hidden ocean worlds that Ceres has revealed to us may represent our first glimpse into this larger biological cosmos, a preview of discoveries that will reshape our understanding of life's role in the universe for generations to come. Generations to come. The revelations emerging from Ceres have fundamentally altered how we perceive the architecture of possibility within our cosmic neighborhood. When we consider that this modest world, drifting silently through the asteroid belt, managed to orchestrate billions of years of complex chemistry while maintaining conditions that could nurture the emergence of life, we begin to grasp the profound implications for countless other worlds scattered throughout the galaxy. Think about the extraordinary resilience demonstrated by the processes operating within Ceres's hidden depths. These weren't fragile systems that required precise conditions to survive. Instead, they represented robust networks of chemical activity that adapted and evolved as their environment gradually transformed over geological time. This adaptability suggests that complex chemistry, and potentially life itself, might be far more tenacious and widespread than our Earth-centric perspective has led us to believe. The gradual transition from Ceres's active ocean world phase to its current frozen state provides a unique window into how complex systems respond to slowly changing conditions. Unlike the catastrophic events that have periodically reset Earth's biological evolution, the chemical evolution on Ceres would have proceeded continuously, allowing molecular systems to gradually adapt to increasingly challenging conditions without experiencing sudden disruptions. This scenario creates fascinating possibilities for what might exist within Ceres today. The molecular networks that survived the dwarf planet's cooling phase would represent the ultimate achievement in chemical adaptation. These systems would have learned to function efficiently in conditions of extreme cold, high salinity, and minimal energy availability. They would be molecular survivors that have been continuously refining their strategies for over 2 billion years. The implications of such evolutionary refinement are staggering. On Earth, organisms that live in extreme environments often develop remarkable biochemical innovations that allow them to thrive where other life forms cannot survive. But these terrestrial extremophiles have had only a few billion years to adapt to their harsh conditions. The hypothetical molecular systems within Ceres would have had twice as long to perfect their survival strategies under gradually worsening conditions. What kind of molecular innovations might emerge from such extended periods of chemical evolution under stress? We can barely imagine the biochemical solutions that might evolve when simple chemistry has billions of years to experiment with increasingly sophisticated survival strategies. These systems might employ energy capture mechanisms, molecular repair processes, and organizational structures that are completely unknown to terrestrial biology. The detection of such highly evolved chemical systems presents unprecedented challenges for astrobiological exploration. Traditional approaches to searching for life rely on recognizing familiar biochemical signatures or metabolic processes. But chemical systems that have been evolving independently for billions of years might operate according to principles so alien to our experience that we lack the conceptual framework to recognize them as organized systems at all. Future missions to Ceres will need to employ entirely new approaches to detecting and characterizing extreme chemical complexity. These missions might need to look for subtle patterns in energy flow, detect microscopic organizational structures that indicate purposeful molecular arrangement, or identify chemical processes that operate with efficiency levels that suggest sophisticated optimization rather than random chemical activity. The development of these detection capabilities is driving revolutionary advances in analytical chemistry and molecular biology. Scientists are learning to recognize the signatures of complex organization at the molecular level, developing new mathematical tools for analyzing chemical networks, and creating artificial intelligence systems that can identify patterns of molecular behavior that might indicate sophisticated chemical evolution. But the significance of Ceres extends far beyond the technical challenges of detecting complex chemistry. This world has forced us to confront fundamental questions about the nature of life itself and how we define the boundary between chemistry and biology. The molecular systems that might exist within Ceres today could blur these distinctions in ways that challenge our basic understanding of what constitutes a living system. Consider the possibility that the chemical networks within Ceres might have achieved levels of complexity that approach or even exceed what we typically associate with simple life forms, yet they might operate according to organizational principles so different from terrestrial biology that we wouldn't recognize them as alive using our current definitions. These systems might represent an entirely new category of complex organization that falls somewhere between chemistry and biology as we currently understand these concepts. The study of such intermediate systems could provide crucial insights into how life emerges from non-living chemistry. Rather than trying to understand this transition by studying ancient fossils or conducting laboratory experiments with simplified chemical systems, Ceres might offer us the opportunity to observe chemical evolution in action across unprecedented timescales and under conditions that don't exist anywhere on Earth. The molecular systems within Ceres represent more than just interesting chemistry. They represent a natural experiment in chemical evolution that had been running continuously for billions of years under carefully controlled conditions. The results of this experiment could teach us fundamental lessons about the principles that govern the emergence of complexity in the universe. These insights have implications that extend far beyond astrobiology. Understanding how complex molecular networks self-organize and evolve over vast timescales could revolutionize fields ranging from materials science to artificial intelligence. The principles that allowed chemical systems on Ceres to maintain organization and function for billions of years might inspire new approaches to creating robust, self-repairing technologies here on Earth. The engineering challenges involved in surviving within Ceres's harsh internal environment could also provide blueprints for developing technologies that can operate reliably under extreme conditions. The molecular strategies evolved by hypothetical Cerean chemical systems might inspire new approaches to designing systems that can function in the deep ocean, in polar environments, or even in the harsh conditions of space exploration. But perhaps most profoundly, Ceres has revealed that the universe might be far more creative in generating complex systems than we ever imagined. The chemical evolution that may have occurred within this world demonstrates that given sufficient time and energy, even the most unlikely environments can give rise to remarkable levels of molecular sophistication and organization. This creativity isn't limited to biological systems. The same principles that might have driven chemical evolution on Ceres could operate in countless other contexts throughout the universe. Complex networks of interacting components might emerge and evolve wherever energy flows through systems over extended periods, creating hierarchies of organization that span scales from molecular to cosmic. The recognition of this universal creativity has profound implications for how we understand our place in the cosmos. Rather than existing as isolated biological anomalies in a largely lifeless universe, we might be part of a vast tapestry of complex systems that includes not only biological life, but also sophisticated chemical networks, self-organizing physical systems, and perhaps even forms of complexity that we don't yet have names for. This perspective transforms our relationship with the universe from one of cosmic loneliness to one of cosmic kinship. We share the universe with countless other examples of complexity and organization, even if most of them exist in forms and locations that make them difficult for us to recognize and study. The chemical evolution that may have occurred on Ceres represents just one thread in this larger tapestry of cosmic complexity. The technologies we're developing to study Ceres and similar worlds are simultaneously preparing us to detect and understand complex systems wherever they might exist throughout the universe. Each advancement in our ability to recognize molecular organization brings us closer to discovering the full scope of complexity that exists in cosmic environments. As we continue to push the boundaries of what's possible in planetary exploration, we're also expanding our understanding of what's possible in terms of complex system evolution throughout the cosmos. The study of Ceres has become a gateway to understanding principles of organization and evolution that operate on scales far larger than any individual world or biological system. The implications ripple outward from planetary science to cosmology itself, suggesting that the universe might be fundamentally oriented toward the creation and evolution of complex systems. Rather than being a rare accident that occurred only on Earth, complexity might be an inevitable consequence of cosmic evolution, emerging wherever conditions allow energy and matter to interact over sufficient periods of time. This view of the universe as a complexity-generating system transforms how we think about the meaning and purpose of scientific exploration. We're not just studying distant worlds to satisfy our curiosity about what's out there. We're investigating the fundamental mechanisms by which the universe creates and sustains the complex systems that make phenomena like consciousness and intelligence possible. The journey to understand Ceres has become a journey to understand the creative capacity of the cosmos itself. In studying how this small world managed to maintain complex chemical evolution for billions of years, we're simultaneously investigating the deeper principles that allow any complex system to emerge and persist in an apparently hostile universe. Each new insight from Ceres adds another piece to our growing understanding of how complexity emerges from simplicity, how organization arises from chaos, and how the universe continuously generates new forms of order and sophistication. The chemical networks that may exist within this distant world represent more than just interesting planetary science. They represent a window into the fundamental creativity that drives cosmic evolution itself. As we prepare for the next generation of missions to explore Ceres and similar worlds throughout our solar system, we carry with us the knowledge that we're not just searching for signs of life or complex chemistry. We're investigating the basic mechanisms by which the universe creates meaning, purpose, and perhaps even consciousness itself through the patient accumulation of complexity over cosmic timescales. The story of Ceres continues to unfold, revealing new layers of significance with each piece of data we analyze and each new theoretical framework we develop to understand its remarkable history. This small world has become a touchstone for our understanding of cosmic complexity, a reminder that the universe is far more creative and purposeful than our limited perspective might suggest. In the hidden depths of a world that was once dismissed as cosmic debris, we may have discovered evidence of the fundamental processes that connect us to the deepest creative forces operating throughout the universe. The chemical evolution that unfolded within Ceres's ancient ocean represents more than just planetary history. It represents a glimpse into the magnificent complexity that emerges when the universe is given sufficient time and space to explore the full range of organizational possibilities. The quest to understand what Ceres represents in the grand scheme of cosmic evolution has led us to grapple with questions that stretch far beyond planetary science into the very foundations of how we understand reality itself. When we consider the extraordinary journey this small world has taken us on, we begin to realize that we're not just studying a distant object floating in space. We're investigating a fundamental principle that may govern how the universe operates at its deepest levels. picture the remarkable cascade of discoveries that began with those mysterious bright spots gleaming against Ceres's dark surface. What started as simple curiosity about unusual reflective patches has evolved into a comprehensive re-evaluation of where complex chemistry can emerge, how long it can persist, and what forms it might take when given billions of years to develop in isolation. Each new piece of evidence has forced us to expand our conception of what's possible in planetary environments. The thermal evolution models that revealed Ceres's billion-year period of internal heating represent more than just sophisticated computer simulations. They represent a window into processes that operated on timescales so vast that they challenge our ability to truly comprehend their significance. When we try to imagine chemical systems evolving continuously for 1,000 million years, we're attempting to grasp durations that dwarf all of human history by factors of millions. Yet within these incomprehensible timescales lie possibilities that are both humbling and inspiring. The molecular networks that may have developed within Ceres's ancient ocean had time to experiment with every conceivable chemical combination, to test countless organizational strategies, and to refine their survival mechanisms through billions of generations of molecular reproduction and modification. The scope for innovation within such extended timeframes exceeds anything we can readily comprehend. What makes this scenario particularly remarkable is the stability that Ceres's subsurface environment would have provided for these evolutionary processes. Unlike surface environments that are subject to cosmic bombardment, atmospheric changes, and stellar variability, the protected depths of Ceres's ocean would have offered conditions of almost unimaginable consistency. Chemical evolution could proceed without the constant interruptions that characterize most planetary environments. This stability would have allowed for the development of molecular complexity that might be impossible to achieve under more dynamic conditions. On Earth, even our most stable environments experience significant changes over geological time. But within Ceres's subsurface ocean, chemical systems could have developed and refined their organizational strategies without major environmental disruptions for periods longer than the entire history of complex life on Earth. The implications of such uninterrupted chemical evolution extend into realms that challenge our basic understanding of how complexity emerges in natural systems. We're accustomed to thinking about evolution as a process driven by environmental challenges and competitive pressures. But the chemical evolution that may have occurred on Ceres would have been driven primarily by the internal logic of molecular organization itself. Without external pressures forcing rapid adaptation, chemical systems on Ceres would have had the luxury of exploring every possible avenue for increasing efficiency, stability, and complexity. This kind of unconstrained molecular evolution might have led to organizational strategies that are completely unknown to terrestrial chemistry, creating networks of unprecedented sophistication and capability. The mineral-rich environment within Ceres' ocean would have provided an almost infinite palette of chemical building blocks for these evolutionary experiments. Unlike the relatively limited chemical diversity available in most planetary environments, the hydrothermal circulation within Ceres would have continuously brought new elements and compounds into contact with evolving molecular systems. This chemical diversity would have enabled forms of molecular innovation that might be impossible in more constrained environments. Chemical systems could have incorporated rare elements, experimented with unusual molecular geometries, and developed metabolic pathways that exploit chemical reactions unavailable in simpler environments. The result could be molecular networks that operate according to principles entirely foreign to our current understanding of chemistry. The detection and study of such exotic chemical systems would require entirely new approaches to analytical chemistry. Traditional methods for identifying complex molecules rely on recognizing familiar chemical signatures and organizational patterns, but chemical systems that have evolved independently for billions of years might employ organizational strategies so alien to our experience that they would be completely invisible to conventional analytical techniques. This challenge is driving the development of revolutionary new technologies that can detect complex organization without making assumptions about what that organization should look like. Advanced pattern recognition algorithms, quantum sensors capable of detecting minute energy flows, and sophisticated mathematical frameworks for analyzing complex chemical networks are all being developed specifically to address the unique challenges posed by potentially exotic chemical systems. But the significance of these technological developments extends far beyond their application to Ceres exploration. The techniques being developed to detect complex chemistry on distant worlds are finding applications in fields ranging from medical diagnostics to materials science. The ability to recognize sophisticated molecular organization has implications for understanding everything from disease processes to the development of advanced artificial materials. The study of Ceres has also revealed important insights about how complex chemical systems might interact with their environments over cosmic timescales. The gradual cooling of the dwarf planet's interior created a natural experiment in how complex organization responds to slowly changing conditions. This scenario provides a unique opportunity to understand how sophisticated systems adapt to environmental stress over periods far longer than any laboratory experiment could encompass. The molecular systems that may have survived Ceres's transition from active ocean world to frozen brine environment would represent the ultimate achievement in adaptive chemistry. These systems would have learned to maintain their organization and function even as their environment became progressively more challenging, developing survival strategies that could operate under conditions that would destroy any terrestrial chemical system. The study of such extreme adaptation has profound implications for understanding the limits of molecular organization. If chemical systems can maintain complexity under the harsh conditions that exist within Ceres today, then similar systems might be able to survive in environments throughout the universe that we currently consider completely hostile to any form of organization. This realization fundamentally expands our conception of where complex chemistry might exist in cosmic environments. Rather than being limited to the narrow range of conditions that support terrestrial life, molecular complexity might be able to persist and even flourish under conditions that span an enormous range of temperatures, pressures, and chemical compositions. The implications extend to our understanding of how complex systems might emerge and evolve in other extreme environments throughout the universe. From the crushing depths of gas giant atmospheres to the radiation-bathed surfaces of neutron stars, the principles revealed by Ceres's chemical evolution might apply to the development of complex organization in contexts that we've never seriously considered. This expansion of possibilities has profound implications for how we think about the distribution of complexity throughout the cosmos. Rather than being concentrated in rare Earth-like environments, sophisticated organization might be emerging and evolving in countless locations where energy flows through matter over extended periods. The universe might be far more systematically creative than we've ever imagined. The recognition of this cosmic creativity has transformed how we approach the search for complex systems beyond Earth. Instead of focusing exclusively on environments that resemble terrestrial conditions, scientists are developing broader frameworks that can encompass the full range of physical and chemical conditions where sophisticated organization might potentially arise. And so we reach the end of this extraordinary journey through the hidden depths of Ceres, a world that has fundamentally transformed our understanding of where life might flourish in the cosmic darkness. From mysterious bright spots to billion-year ocean worlds, from indigenous organic chemistry to the tantalizing possibility of molecular systems that blur the very boundaries between chemistry and biology, Ceres has revealed that the universe may be far more alive than we ever dared to imagine. If you found wonder in these cosmic revelations tonight, I'd be grateful if you'd share this journey with others by hitting that like button and subscribing for more explorations into the mysteries that surround us. Until next time, keep looking up at the stars, knowing that in the darkness between worlds, extraordinary secrets are waiting to be discovered.